In the previous lecture, we have seen that the speed of sound is not a real limit for aerospace. You may ask, are there any limits to the airspeed? This lecture is about the limits of speed and the challenges of flight at hypersonic speeds. When we would like to fly at high speed, we need to have sufficient power to propel the aircraft. Also, we know that higher speeds will induce higher drag. In the previous lecture, I told you about drag caused by shock waves, when the aircraft flies faster than the speed of sound. In addition to that, also the friction drag will become very high. This friction causes high temperatures of the skin of the aircraft. Therefore, we need special materials. The aircraft shown in this picture is the X-15. It is powered by a rocket engine. This engine brings the aircraft to speeds as high as 7,274 kilometers per hour, or a Mach number of 6.72. At that speed, the skin temperature becomes so high, about 650 degrees Celsius, that common alloys are not applicable. In this case, the engineers use special alloys like titanium, stainless steel, and special steel alloys like Inconel. Aluminium alloys in this case are no option. They will melt at this temperature. The example shows that at high airspeeds, a high temperature may occur due to friction. At high temperature has a negative impact on the performance of most materials. Aluminium alloys can be used up to temperatures of 100 to 120 degrees Celsius. Beyond 150 degrees, most strength values drop very rapidly. Also, most composites cannot sustain temperatures higher than 150 to 200 degrees Celsius. If we need an aircraft material for high temperatures, we have to look for materials like titanium alloys or specific steel alloys. In this respect, titanium is favorable because of its low density, which is 4,500 kilos per cubic meter. This is much lower than for the steel alloys. In this picture, you see the relative values for the ultimate strength and the yield strength of a titanium alloy as function of the temperature. Reading from this plot, we can see that there is a significant drop in values at about 150 degrees Celsius. After that initial drop, the properties decrease slowly. At, for example, 500 degrees Celsius, still more than 50% of the room temperature property values remain. Another famous example of a high temperature application of titanium is the SR-71 Blackbird. This aircraft, which is a military reconnaissance aircraft, could fly at high speed and high altitude. The speed was well over Mach 3. Because of the aerodynamic heating of the skin and structure, more than 90% of it was made of titanium alloys. Just as an indication for the temperature, the leading edges are exposed to temperatures of more than 400 degrees Celsius. And after landing, the aircraft needed quite some time to cool down. This picture shows the Concorde. This aircraft made its first flight in 1969. It was made in a joint venture by France and Great Britain. The Concorde, a civil aircraft flying at the speed of Mach 2, was made of aluminium alloys. The choice for aluminium alloys was related to its maximum speed. If the aircraft would have been designed for higher speeds, other materials would have to be selected. If we look at space applications, we encounter different limits to materials. First of all, when the space vehicle returns to the Earth, making a re-entry into the atmosphere, the temperatures are extremely high. I will come back to this in a few moments. In space itself, where no air exists, there is no friction. The material heats and cools down only when the surface is turned to or turned away from the sun. However, the materials are exposed to other threats, like radiation and high velocity impact of small particles. Designers of space vehicles should also make precise energy balances. When heat is entering the vehicle, it should be absorbed or radiated back into space. When space vehicles make a re-entry into the atmosphere, the friction is very high, and so are the temperatures. Without special measures, temperatures could be as high as 2000 degrees Celsius. This is too high for almost any material. However, some ceramic materials can sustain these high temperatures. In the past, a lot of space vehicles had ablative shields to absorb the high temperature and to dissipate the energy. By sublimation of the shield, so by pure sacrificing, the energy was absorbed. So the shield became thinner when the spacecraft entered the atmosphere. The space shuttle used other materials to cope with the high temperatures. Its thermal protection system consisted of special carbon-carbon composites, special tiles, and heat blankets. Each area had its own material. The hotter sections, the nose and the leading edges, were made of carbon-carbon composite, a hard but brittle material that can cope with temperatures exceeding 1650 degrees Celsius. However, the brittle nature of the material also took its toll when the shuttle Columbia disintegrated during re-entry, because the leading edge was damaged. Another famous material applied on the space shuttle are the black tiles. See the picture on the right. These are made of lightweight silica materials, with a lot of air included. The outside is of carbon layer. Most tiles were applied at the lower surface of the space shuttle, and most tiles had unique dimensions. So let's summarize our current records. Are there speed limits? There are, to some extent, although these are not absolute limits. The fastest aircraft flew more than 7,000 kilometers per hour. The highest altitude for an aircraft is 112 kilometers for the Spaceship One. We also know about the Voyager, an aircraft that flew non-stop around the world. And all these records can be improved. However, if we want to push these limits, we need to think about special designs and special materials.